All right, we are on chapter 10. We've been talking about carbonyl hydration. We had this discussion last time about the extent of nucleophilic attack versus protonation in the rate determining step of a general acid catalyzed mechanism. And we said, interestingly, that for carbonyl hydration, the evidence is you increase the strength of the acid, and what that actually does is it moves your transition state towards less nucleophilic attack. In a general acid catalyzed transition state where you have nucleophilic attack at the same time as protonation, if you use a stronger acid, apparently you don't need as much nucleophilic attack before the acid protonates the oxygen. Okay, so subtle interplay of issues, and that's the whole point of chapters 10 and 11. We're looking at the intricacies of mechanism that were under the surface that you were just skimming over merrily on your OChem water skis and didn't know the depths that were to deal with. I want to mention just a little bit about thermodynamics of acid catalyzed carbonyl hydration. Whoops. To give you a sense for steric and electronic issues. So what I'll show you here is a comparison of equilibrium constants where this is basically the concentration of the gem diol, the hydrate product, versus the carbonyl containing compound. And we'll show you that for various carbonyls. So formaldehyde, the equilibrium constant dramatically favors the hydrate by a factor of 2,000. But you put those CH3 groups on there and you go down, the equilibrium constant decreases by 6 orders of magnitude. So what's your rationale for that? Why do you see less hydrate for the ketone than for formaldehyde? Yep, electron poor, good. And how do you know that?
Because carbons are more electron donating molecules.
Okay, right. So there's two reasons. There's two ways that a CH3 group can donate electron density. One is inductive. That has to do with the fact that sp3 hybridized carbons are less electronegative than an sp2 hybridized carbon, and so these can donate inductively through the sigma bonds. There's also another effect going on here. We haven't talked about it, and I'm not going to draw it, but what's the LUMO of a carbonyl? Pi star, right? That's an empty unfilled orbital. On this adjacent alkyl group, you have carbon-hydrogen bonds. So you can have a stabilizing sigma to pi star hyperconjugation. In addition to that, inductive donation. Both of these will tend to spread out the LUMO. The hyperconjugation effect will tend to raise the energy of the LUMO, spread it out, make it less reactive. So those are both reasons why the ketone is less reactive than the aldehyde. Of course, we can play around with these sort of cute effects all day. We can we can add electron withdrawing groups, and then that's going to bump up the equilibrium constant again. Why? Because of inductive withdrawal of those chloro groups. So there are other comparisons we could make, I think, but that sort of gets the point. Another issue is the issue of strain in carbonyl additions. We'll come back to carbonyl additions a little bit later, but while we're talking about hydration is a good time to think about this. The equilibrium constant I'm going to show you here is not for the hydration reaction, but for hemiacetal formation. So we're going to have at equilibrium concentration of hemiacetal. It's the methanol hemiacetal, in case you're curious. And so we'll do that and then structure. So here is, oops, I can't draw a square, cyclobutanone, and we're showing you relative equilibrium constants, so that's 1. I'm not totally sure how these equilibrium constants on the right compare to the hydration equilibrium constants on the left. They're from two different papers, so you shouldn't worry about trying to compare the numbers directly. Notice that the constant is high for cyclobutanone and it's relatively low for cyclopentanone, a little bit higher for cyclohexanone. What do you think what's the explanation here? Any ideas? Okay, ring strain. Let's talk about hemiacetal versus carbonyl. Hemiacetal would be this. What's hybridization in the hemiacetal? Right? Versus at the carbonyl carbon, it's sp2 for the ketone. Bond angles of 109.5 versus 120. Now compare those endpoints to where the polygon of that size wants to be, 90 for the cyclobutanone. So there's significant release of ring strain when you go from sp2 to sp3 for the cyclobutanone, okay? Not quite as much for the 5-membered ring. I forget what the target, I should know this, but I don't care to remember it apparently. But the target angle for a 5-membered ring is,
I think it is
100 and something. Anyway, there's an equation.
I think it is 120.
Is it? I thought it was definitely 120 for the 6-membered ring. Now we have to Google it.
It's 108, yeah.
Ideal angle for pentagon. For a regular pentagon, 108. Yeah, you're right. So, there's less. So if the ideal angle here is 108 versus 90 here, you're not quite so bad when you're constrained at 120. Does that make sense? So you're not relieving as much ring strain when you go from sp2 to sp3 for the 5-membered ring, and then for the 6-membered ring, the magnitude gets a little bit higher. But you have to remember that, let's see, in the 6-membered ring, the ideal angle is 120. But you've also got issues of conformation, right? That's layered on top of this simple issue of angle strain, right? Because the 6-membered ring, if it were flat, it would prefer 120 angle. But of course, it can twist and form the chair, in which there is no angle strain. In contrast, 5-membered rings, conformations are far more flexible. And so, anyway, the idea is that when you're thinking about carbonyl additions to rings, you have to think about not only ring strain, but also the various steric interactions you introduce, whether something's axial versus equatorial, and other things. Okay. I don't know that there's too much. The book didn't say too much about this trend. It sort of presented the data and said that ring strain makes a difference. So I don't know that it's worth parsing that out at a lot of in a lot of detail. Anything else you want to say about that? Okay, so we'll now do the reaction where in 351, the reaction happens about now, maybe a little bit earlier on in October when people are taking 351, and it's where everything just starts to go off the rails, and that's alkene hydration. And your standard, we'll do alkenes and alkynes actually, but your standard mechanism is, here's your alkene, the rate determining step is protonation of the alkene. You've seen that before. Then tell me what the intermediate is.
Tertiary carbon.
Tertiary carbocation with the new bond with the proton there. That's called Markovnikov regioselectivity. You get the positive charge on the more substituted carbon where it's more stable, right? Because of hyperconjugation between the adjacent carbon-hydrogen sigma bonds and the empty p orbital. At least that's the explanation. Also, often there are multiple things going on. Probably it's also related to the fact that alkyl groups are inductive donors. Again, you've got a situation where you've got sp3 carbons adjacent to an sp2 carbon. Then water adds to the more substituted carbon where the positive charge is. You get this oxonium ion intermediate, which then in a final fast step is proton is, oops, I don't want the red color there. Proton is removed to regenerate your acid, and this is why it's an acid catalyzed reaction. Sorry about the positive formal charge. And then your final product is an alcohol. Okay, that's sort of the standard mechanism. This is, as you can see, protonation is involved in the rate determining step. So this is general acid catalysis. If you do the kinetics of the reaction, as you would predict, it is first order in olefin, which is just another word for alkene, but it sounds like oliphant, which is what Sam Gamgee says is how you talk about elephants. I'm almost done with the Two Towers. I'm reading it for the first time in like 20 years, and it's kind of fun. Let's see, and it's also first order in acid. Another way you can tell that this is general acid catalysis is there is a strong primary kinetic isotope effect. If you do hydrogen versus deuterium for the acid or whatever proton donating species, it's like 6, which is pretty close to the theoretical max, which tells you that proton transfer is a big part of the rate determining step. We've talked about Markovnikov regioselectivity, meaning that you get the positive charge, you get the thing that adds, the non-hydrogen thing that adds ends up on the more substituted carbon. That's all related to this carbocationic intermediate. But there's some interesting data in the text that are really kind of cool here. They did a Hammett-type analysis of olefins that are substituted like this. So there's an X group and a Y group. And they measured the rate of olefin addition as a function of this term, the sum of sigma plus values. Now, if you remember when we first introduced Hammett analysis, sigma plus is how good something is at being an electron donating group versus withdrawing group by resonance. I guess they're doing something to the air. Anyway, so they're adding together. You've got an olefin, and on the same carbon, you've got 2 different substituents. Wow, that's kind of...
Does this like once a week?
Yeah.
Less.
When they were first getting the system set, like it would be insanely cold in the offices because they'd be blowing cold air. Yeah. Anyway, so this is going to be the sigma plus value for the X substituent versus the sigma plus value for the Y substituent. And they plot the rate versus these sum of these sigma plus values, the sum of them, and you get something that's linear, which tells you that the electron donating group versus electron withdrawing group effect is additive if the substituents are on the same carbon. Now, why would we care about that? And what does that tell us about the transition state for this reaction? Let me just show you some example data sort of selected from this study. And we're going to do rate of the reaction. It turns out that the rate for the monosubstituted alkene is about the same as the rate for the 1,2 disubstituted alkene. Okay? That rate is about the same, and that's true for, we'll just put cis and trans sort of same there. But if you have a 1,1,2 trisubstituted alkene, the rate goes way up. And but if you have the 1,1,2,2 tetrasubstituted alkene, not so big of a difference. Okay? In other words, the impact of adding substituents is only additive if they're on the same carbon. Okay. Why does that make sense? What does that tell you about the transition state for this rate determining step? What does it tell you about that carbocationic intermediate? Okay, right, it sits on the more substituted carbon and it's localized, which means that substituents over here don't matter as much. You might have, and so let's sort of draw what the transition state might look like that could explain this. Actually, we'll do it with a disubstituted alkene. No, let's just do it with a trisubstituted alkene. Sorry, making different decisions. So that's the transition state, and there's a buildup. There's definitely one of the two carbons that has a bond, forming a bond with the hydrogen, and the other one is getting the positive charge. Now, we talked a long time ago about an alternative possibility, and this is that you have some sort of bridged carbonium ion type intermediate where both of the carbons bear the positive charge, right? Because we talked about how in some cases for carbocations, this is the right structure, right? A three atom, two bond, three center, two electron bond, where two electrons are delocalized between the carbons and the hydrogen. Where the alternative proposal here for the transition state is something like that. And if that were true, you would expect substituents on both carbons to matter additively, because both carbons are bearing positive charge. But this is the one that is consistent with the data. This is why this one, the trisubstituted olefin, is so much faster than any of the disubstituted olefins, because as far as the transition state's concerned, a 1,2 disubstituted olefin is exactly the same as a monosubstituted olefin. There's only one substituent on the carbon that can bear the positive charge. Does that make sense? So this is evidence that you've got a localized carbocation in your transition state. Yeah?
What if you compare a gin substituted with a tri-substituted?
Right. So that would be like, and wasn't listed in the comparison. Yeah, I don't know. That's the one you're asking about, and I'm not sure where that fits. I would predict faster than this, but probably about the same as this, actually. Yeah. We can look it up, but my guess is it fits there. Yep. Okay. So there's not too much more to say on olefin hydration. You can do alkyne hydration as well, and depending on the OChem text you used for your introductory class, that may have been in a separate chapter or in the same chapter. Generally, again, it's general acid catalyzed, rate determining proton transfer. Alkyne hydration is a little bit slower, in part because the intermediate you form is called a vinyl carbocation. You have a positive charge on an sp hybridized atom that's more S character. sp hybridized carbons are more electronegative than sp2 hybridized carbons or sp3 hybridized carbons. So it's actually higher up in energy to get to the vinyl carbocation. Nevertheless, these reactions work. The initial intermediate is called, the initial product, sorry, and I'm omitting a proton transfer step that regenerates hydronium, if that's okay. Your initial product is an enol, and then you tautomerize to get the methyl ketone. That's if you're using this terminal alkyne or an acetylene. And so the same general principles apply. When the alkyne is an acetylene, you get the positive charge on the more substituted carbon where it's more stable. That's again Markovnikov regioselectivity. One thing that your text points out about both of these reactions is that this rate determining protonation is irreversible in the sense that the subsequent steps are so fast. So you can do isotope scrambling experiments to demonstrate that actually there's no removal of the proton after it gets added. I won't talk in detail about that, but both of these tend to be irreversible because the subsequent steps are so fast. Another piece of evidence for a carbocationic intermediate is that if you do the Hammett analysis for a phenylacetylene, we'll have some X group there, and then here's your alkyne. Sorry, don't love that. The rho value for this particular reaction is minus 3.8. Okay, now remember that the original reference benzoic acid reaction for Hammett analysis is related to benzoic acid deprotonation. Positive rho values tell you this reaction involves buildup of negative charge. Negative rho values tell you that this involves buildup of positive charge. So this is highly sensitive to, much more sensitive than the benzoic acid reaction is, and that's because you've got an intermediate, which in this case is directly conjugated to the ring, so electron donating substituents can make a big deal. All right, anything you want to know about that? Questions? This isn't that synthetically useful because it involves a strong acid, and there's a lot of other things that can happen to strong acids. Nevertheless, the mechanistic details and intricacies are useful and apply in a lot of other cases. All right, I feel like we're doing all of like chapter 10 from 351 in a single day, so that's fantastic. Next is what you would expect. I guess I didn't need to draw the line there, oh well. Hydrohalogenation, or electrophilic addition of hydrogen halides to alkenes and alkynes. And this is section 10.4. Your standard mechanism here is add HCl, pi bond attacks the HCl sigma star to give you a carbocationic intermediate, which then Cl comes in and attacks to give you the corresponding chloride. Okay. General issues, we expect Markovnikov regioselectivity because you've got a carbocationic intermediate. So in this case, I didn't show you an example where we had an issue between the more versus less substituted carbon, but generally chloro ends up on the more substituted carbon. Relatively simple. The first step is rate determining step, rate determining protonation. Let's talk about some mechanistic complexities. We'll deal with some general kinetic observations first. The reaction is generally first order in HCl and in alkene, which is again evidence for a general, actually we wouldn't call this general acid catalysis anymore because we're not regenerating our acid. So, bloop. But proton transfer is involved in the rate determining step. The kinetic isotope effect, if you do Kh over Kd, for hydrogen versus deuterium in the protonation step is around, probably with two significant figures, we'll just use an equal sign, three significant figures anyway. That's for HCl versus DCl. Okay, so that's a primary kinetic isotope effect, but it's a small one. Why it's that way why it's not larger than that may reflect the force constant in the transition state between the new carbon-hydrogen bond and the old hydrogen chloride bond. But that's generally interpreted as evidence for, along with the fact that it's first order in HCl, for the fact that you're changing bonding with a hydrogen in the transition state. I will say that, of course, you can't just add HCl by itself to a reaction mixture because HCl is a gas. Using HCl in water is not generally preferred for this reaction because then you're going to be competing with hydration. One of the solvents that's generally used is acetic acid, and that introduces some issues that demonstrate how complicated this mechanism is. So ACOH is acetic acid. So let me give you an example that demonstrates this complexity, and we'll sort of dive into this. Here's a starting material. HCl is the acid, and then acetic acid is the solvent. And we see the following products. In a 2:2:1 ratio. Okay, so let's talk where each one comes from. How about this one? Where does that one come from, the first product? Just straight up Markovnikov, protonate the pi bond, get the more substituted carbocation, and then chloro attacks. All right? How about this one? Dun, dun, dun. Carbocation rearrangement. Why did that happen? If this is the carbocationic intermediate, what are we talking about? Yeah, a 1,2 methyl shift. To give you, and why would that happen? What's a driving force for a 1,2 methyl shift? carbocation stability. And that's literally just a methyl group with its electrons leaning over, going through a 3-centered, 2-electron intermediate transition state, intermediate, not sure what the potential energy landscape is, to give you this carbocation intermediate, and then chloro attacks at the more substituted carbon. Yeah, your driving force there for rearrangement is you get a more substituted carbocation that's more stable. Good, we're still recording, excellent. How about this one? Where'd this one come from?
Acetic acid.
Right, acetic acid is now competing with chloro for this carbocation intermediate. So this gives you some sense as to how long carbocation rearrangement takes, that at least attack of chloro and of solvent is somewhat competitive with rearrangement to give you the more substituted carbocation. You know, depending on how much solvent you add and how much chloro you add, you might have this idea that solvent should be able to compete with chloro, right? Yeah.
So technically, in our general OChem class, we wouldn't have been wrong if we had missed the methyl shift.
Would you have been wrong? I probably, yes. If you missed the methyl shift, you would have been wrong.
No, you'd be half wrong.
That's true. You would be half wrong because you do see this, and that's why if you really push a introductory OChem professor, they're going to hedge on this. I tell students I want you to draw the rearranged and the unrearranged products. Some texts will present it as though you only see the rearranged product, and that's not reality. Yeah.
So it's like half and half.
Yeah. Go ahead.
Can you say again why we don't see the carbocation rearrangement with the
Acetate?
yeah.
I don't know. It's possible that it's there, but in small enough amounts that they didn't characterize it. It's possible they didn't look for it. But the issue of the extent to which acetate competes with chloro is actually one of the intricacies we want to get to. So if you did this in the lab and you really, really wanted the chloride, one of the first things somebody would suggest, well, actually, you tell me, what should I do if I want to have more chloride than acetate? Throw in a bunch of Cl minus, right? So let's look at the effect of added nucleophile, added Cl minus in whatever form. Or maybe you, instead of, since you could add Cl minus, or maybe you figure maybe I just need to add more HCl because of course the Cl minus I thought that comes in and does the attacking comes from HCl. Turns out in this case the product ratio is totally independent.
No. What?
Totally independent of added chloro and HCl. You can't make this stuff up, right? And you would think that added chloro should compete with acetate for the carbocation. And the explanation involves something that we probably haven't considered before, and that is something called a contact ion pair within a solvent cage. All right, so rate determining protonation of, normally when we draw the mechanism, as I did above, I just drew, hold on, no, that's still a right carbon, okay. I normally would have just drawn this intermediate, and we forget about the chloro, right? Because in introductory OChem, we don't care about counter ions for the most part. But in reality, what happens is before you get to this intermediate that's fully solvated and the carbocation is off at sort of infinite distance, I'm going to get rid of the hydrogens to simplify my drawing, but we're going to keep the positive charge in the right spot. Before that goes away, before chloro goes away, you have this intermediate which we call the contact ion pair. That means the chloro is still around. It doesn't go very far after this initial step. Okay? So we form the carbocation and chloro is still there. And what do we mean by there? Well, if you think about before and after that reaction step, before, all the molecules were surrounded by solvent, right? There were solvent molecules in the immediate vicinity. They're still there. So the contact ion pair is what happens before the chloro diffuses away. So from this stage, you have two sort of options. You have escape the cage. Escape, it's spelled just like escape. You can escape the cage, and there's some timer on that. How long it takes. That looks like cheese or a pie. It's supposed to be a clock, but whatever. Or you can have attack. Okay, if you escape the cage, then you end up with chloros far away, and now your carbocation is solvated and surrounded by solvent molecules. If you go directly back in and attack, that gives you this. Okay? So what that tells you, the fact that the product ratio here is totally independent of added chloride, tells you that diffusion of the chloride away is very slow relative to two things. And I'm going to modify the drawing that I just did here. It's slow relative to carbocation rearrangement. Okay, so carbocation rearrangement can happen during the lifetime of the chloro escaping the cage. Sorry, during the lifetime when chloro is still around, you can have the 1,2 methyl shift. And it looks like we're going to need a little bit more space, because what I'm going to do here is just show you that during the lifetime of the chloro in the solvent cage in the contact ion pair, rearrangement can occur. If chloro attacks prior to rearrangement, we get this. If chloro attacks after rearrangement, we get this. It's only if chloro escapes the cage that we get acetate attacking. Now, again, I can't answer the question, why don't we see any rearranged acetate product? That's a good question, and the idea is if rearrangement's faster than the contact, if rearrangement happens and this goes back and forth within the lifetime of the contact ion pair, you would certainly expect it to happen by the time we'd gotten there. So why they're not reporting that why they're reporting that they don't see acetate product, I got nothing. Yeah.
Could we manipulate this by using different solvents with different polarities, so that like the cage or the ion pair would just have different stabilities?
Yeah, could you manipulate this by changing the solvent? Absolutely. You can even do it by, I think you're going to hate this, but you can even do this by changing the structure of the alkene. So subtle structural changes create different situations, and you have to be prepared for these sorts of issues. So if you do the same reaction, HCl with acetic acid as solvent, and in this case there's no chance for carbocation rearrangement, but you've got two potential products. Here, product ratio is in fact Ration, no, ratio, there went the O. Ratio is sensitive to added chloride. So subtle structural differences in the molecule influence the lifetime of the contact ion pair, which influences the product ratios. The text makes the point that the reason added chloride doesn't make a difference here is because most of your products come from the solvent cage, and that chloro is not in equilibrium with bulk solvent. All right. So, yeah, go ahead, Logan.
Okay, so is the acetate not protonated? Is the protonated form of the acetate not like the doubly protonated, I guess? Is that not the thing that is donating the proton a lot of the times?
It could be. You'd have to look at pKa's to figure that out. You're talking about this one?
I'd be surprised if that was a...
Yeah, probably.
HCl.
Yeah. Though, actually, this would suggest that not.
Yeah.
And pKa's for HCl in any case were not measured in water. And what the pKa of acetic acid is in pure acetic acid, I'm not sure necessarily. Yeah, it's a good point. Okay. Though acetic acid is certainly less polar than water, and so pKa should go down for HCl at least. For something going. Remember, in less polar solvent, if your acid goes neutral to negatively charged, in less polar solvent, the pKa is going to go down. Going to be less acidic. Okay, there's just a little bit more of complexity in this horrific sort of reaction. We haven't dealt with syn versus anti. We haven't dealt with, and we didn't deal with it with alkene hydration. Syn versus anti relates to does your proton and your chloro add to the same face of the olefin or opposite faces? And you were taught in your introductory class that, well, there's no syn versus anti selectivity because you have a carbocation intermediate, which is planar. And so the nucleophile in the second step can come in from above or below. Asterisk. Okay. So let's, and the consideration of stereochemistry actually illustrates some of these contact ion pair issues even better. So here is a deuterated substrate that will allow us to detect some of these stereochemical issues. Again, we're going to use HCl and acetic acid. Your first product is this one. This one has the hydrogen that was added on the same side as the deuterium. And so we'll call this the syn product. The formation, they actually monitored, there's several products here and they monitored their kinetics separately. This must have been pretty challenging, and I didn't read the paper, so I don't know what was done. Second order kinetics, first order in olefin, which makes sense, and first order in HCl. And the rationale for why it is syn is that this happened via the contact ion pair. Notice the second order kinetics tell you that this is sort of concerted. There's not a carbocation intermediate. Go back to your, oh, sorry, no, I said that wrong. Sorry, even if there were a carbocationic intermediate, you would still expect first order in olefin, first order in acid. But the rationale for the syn stereochemistry there is that the reaction happens from the contact ion pair. I'm sorry, not that it's concerted, but that you have, well, there's probably two possibilities that are consistent with this. One is a fully formed bond between hydrogen and carbon with a full positive charge here, but a chloro that has not yet a chloro that has not yet dissociated and is still on the same side of the olefin and recombines fast enough that there's not time for rotation around the carbon-carbon bond. So fast attack from, or not time for the chloro to diffuse to the other side of the molecule. So fast attack from the contact ion pair that is faster than the chloro could move to the other side of the molecule. Another possibility that would be consistent with this data would be that you have some sort of concerted but maybe asynchronous, meaning not at the same time, transition state that involves a buildup of positive charge on one of the two carbons. We start to form that bond. We get delivery of the chloro to the same face as the hydrogen was delivered to. So both of those transition states could explain the second order kinetics and the syn stereoselectivity. I'll show you one of the anti-products here. There's more that we probably won't have time for today, but we'll hit next time. This is where the hydrogen and the chloro, I'll just, oops, that's not what I wanted. I'll highlight, oops, that's also not what I wanted. What's going on here? There we go. Hydrogen chloro, that's a syn product. Hydrogen chloro, that's an anti-product. The colors are thwarting me today. All right, so this is an anti-product. This one shows third order kinetics. Now that's weird because the mechanism we just showed you above says in the first step, rate determining step, we protonate the alkene and that's it. This is first order in olefin, first in acid, but also first order in chloride. Okay, and that suggests not a carbocationic intermediate, but perhaps a transition state that looks like this, where at the same time as you're protonating the alkene from this side of the molecule, chloro is coming in from the other side of the molecule. And that's weird, in part because you have three things happening at once. Termolecular or three molecular collisions coming together are really rare. So likely what has to happen is that the hydrogen, the HCl complexes the alkene first, some weak loose complex that doesn't proceed to full protonation until the chloro comes in from the backside. Okay, so it's, again, this is more complicated than we taught. We taught you there was a carbocationic intermediate. These first two products say, maybe not if you can avoid it, either through the contact ion pair or through syn delivery of hydrogen and chloride to the same face of the alkene, or through precomplexation of the acid and then attack of chloro from the other side. Okay, so, and the question is, how do I know what's right? Well, you do the experiment to figure it out. And that's one major point of this whole chapter is arrow pushing is a hypothesis. And you need data to support your hypothesis. Okay, so we got to stop there for today. I will post this video on Learning Suite later. I have to take it from iMovie. I have to take it from QuickTime, render it in iMovie, and then upload it. So that takes just a little bit of time. But I'll have that done later today. And I will see you tomorrow.